This next problem is about pressure vessels. That's like some kind of tanker or whatnot where it has pressurized gas or liquid inside. And in this particular case, we're trying to solve for our pressure. But we also have a torque on each side, which consequently, since torque and pressure are only forces, it's going to be the same forces anywhere on this whole entire side. Not on the ends, but we just talk about the sides here. So we want to solve for our max pressure. Alright, first thing that we have to do is solve for our stress element forces. That's sigma x, sigma y, and tau xy. Sigma x is not affected by our torque, only by our internal pressure, so that's going to be PR over 2T. Our sigma y is not going to be affected by our torque either, but internal pressure is going to affect our sigma y. Our torque does, however, affect our tau xy. Our internal pressure does not affect our tau xy. So this is TR over IP. Now, in the last video we talked about our equation T equals VQ over IB and how that was negative. If you haven't seen that one, go watch it real quick. And we just do a little comparison real quick. VQ over IB, that ended up equaling a negative tau xy, because our bottom face, this was defined as positive tau for this formula, and that ends up being a negative tau xy orientation. However, TR over IP is defined for this up, the right side of our element being in the positive orientation, which also happens to be a positive tau xy. So that's a possible sign error if you don't get that straight. So negative tau xy, positive tau xy. We don't have any kind of shearing going on, so it's just our TR over IP. Remember, our IP is different than our IX. We have a circular cross-sectional area. However, this is also a thin-walled tube that we're talking about. So that means our IP, we have used the approximation for thin-walled tubes. It's 2 pi r cubed t. That's something you just have to either look up or memorize. So our tau xy is going to be t, and then the r cancels out with that r, and then it'll be over 2 pi r squared t. Okay, so now we have the easy part is finding out what our sigma x, sigma y, and tau xy are. We just wanted it symbolically, so we're good there. Now comes the hard part. If we have some kind of allowable tensile stress, that means we're looking for our sigma 1. On our Moore's circle, and I'm going to assume it looks something like this, we're looking for our largest value, which is going to be always going to be sigma 1. That's our largest principal stress right there. Some people accidentally use sigma 2 and that's wrong. It has to be sigma 1. That's going to be the thing that breaks. It's going to be the stress that breaks our material first. So sigma 1 has an equation. Let's just write that real quick. So another situation would be, what happens if my sigma 2 is greater negatively than my sigma 1 is positively? Then shouldn't sigma 2 break first? Well, that's both true and untrue. Let me explain. So we're specifically given a sigma allow for tensile strength. That means that it has to be in the positive range. At least one of our, for these kind of problems, at least one of our values here is going to be positive. At least we need it to be positive. This stress is all about failing in tension. If it's failing in compression, that means it might buckle or something else like that. It's going to be, we'd have a different compression strength than tensile strength, depending on the material. Usually they're the same, but it can be different. Again, outside the scope of this class, but interesting. All right, let's plug in some of our values here. Sigma 1, which I'll say is equal to sigma allow, equals PR over 2T plus PR over T all over 2, and this is PR over 2T minus PR over T over 2 squared plus T over 2 pi r squared T squared. Alright, what was our objective again? We're looking for maximum pressure, right? So this is going to get a little bit ugly because I want to isolate my P. So let's try to work through that. Sigma A equals, try to isolate that there. I got 1/2 plus 1 gives me 3/2, divided by 2 gives me 3/4 R over T. Plus, this is 1/2 minus 1 gives me a negative 1/2, divided by 2 gives me a negative 1/4. That's P R over T squared plus T pi R squared T. Keep in mind that the big T is torque, small t is thickness. I'm going to subtract this term to the other side and square both sides. Alright, this is going to end up being A squared minus 2 times sigma A times 3/4 P R over T plus, that's 9/16 PR over T, that's quantity squared, and this is just what it is here. I'll just take the negative out since it's going to be squared. Alright, so this, at least I got rid of the root. Now I need to solve for P. So now I just have to isolate P, and it looks like I'm going to have some kind of quadratic. So let me try to write it in the form of ax squared plus bx plus c equals 0. So 9 minus 1 is 8/16 P R squared T squared P squared minus 3/2 sigma A R over T times P plus the quantity sigma A squared minus T 2 pi R squared T. This algebra is getting a little bit messy, but we are in fact doing this correctly. This problem is going to look messy no matter how you do it. Okay, now quadratic formula. P equals negative B plus or minus. Now, plus or minus, I can actually decide which one right now, since I'm looking for the maximum pressure. The plus and the minus are both going to give me a pressure that would solve this formula, but I'm looking for the max pressure. So let's just say plus. Oh, negative B plus or minus the square root of B squared. Or, yeah. Minus 4 times A, which is R squared over 2T squared, C, which is this big thing, all over 2 times A, which is just R squared over T squared. Alright, and I'm just going to leave it like this because that's pretty nasty. And I could go through and multiply everything by T squared. But you get the idea of how to do this problem. So just to recap, since this was a long one, we find our elemental stresses and we plug that into our formula for our max tensile stress, and then we solve for whatever variable we're looking for. And that's it.